Hello, thank you for joining us. My name is Salish Khangaonkar, Coastal Ocean Modeling Program Manager at PMML, and also serve as the Director of the Salish Sea Modeling Center at UW Tacoma. I'm joined by my colleagues Adi, Sukyang, and Lakshita from the Salish Sea Modeling Center, and also Julie Kister from UW Oceanography and Julia Boss of Washington State Department of Ecology. My talk today relates to assessing impacts of a Pacific marine heat wave on the inner waters of the Salish Sea. The heat wave, Northeast Pacific marine heat wave, was first noticed by Nick Bond of NOAA when a large mass of warm water occupied the Northeast Pacific during the winter months. But what was unusual is that this warm water persisted near the entrance to the Salish Sea for almost 2 years. Naturally, there was concern that these warm waters would propagate into Salish Sea and result in ecological impacts. And that is the motivation for this work. The heat wave itself had characteristics in terms of elevated temperatures that were very similar to projected elevated temperatures for the high emissions scenario for climate change impacts. During the heat wave, there were quite a few reports of ecological impacts along the coast, harmful algal blooms, bird kills. But within the Salish Sea, the reports of impacts reports of effects were limited to observations that there was higher biological productivity, higher zooplankton, which led to perhaps higher herring biomass. The effects were not quantified. So we decided to take a modeling-based approach. The model we use is Salish Sea model that uses FVCOM for hydrodynamics and FVCOM ICM for biogeochemical calculations. The model was set up for a 5-year period from year 2013, from before the heat wave to end of 2017 after the heat wave. So the existing conditions include the heat wave effects, and they reproduced observed data very well and very good skill statistics. But to differentiate it from reference, what we did was we took out the heating during the heat wave. During the heat wave, we found that the net heat flux going into the model from the surface was almost 20% higher. And so we took that down to conditions to match before and after the heat wave. In the same way, the propagation of heat from the ocean boundary, we brought it down to reference by specifying a climatological ocean boundary based on a 10-year average from 1999 to 2009. And the difference between the two gives us the perturbation of how much warmer water or the warm water pulse, how did it propagate into Salish Sea? And we see at the ocean boundary, temperatures of almost over 3 degrees propagating into the Salish Sea. But as the water propagates in, the mixing reduces the high temperatures down to less than 1 degree elevation over normal conditions. But it's important to note that these higher temperatures lasted for almost 2 years from 2015 till the end of 2016. Now, during this time, both model and observations do show increased biological activity as observed in the data. The model also shows higher biomass for phytoplankton and zooplankton. We also found that the volume of hypoxic water increased during that time. But a comparison of existing plot and reference plot shows that both conditions show elevated biological activity, and both reference and existing show higher biomass. This led us to believe that perhaps this increased biological activity is a coincidence. Concurrent with the marine heat wave, we had higher hydrologic loads that came in towards the end of 2014 into 2015, 16, and 17. The higher nutrient loads accompanied by an increase in the strength of exchange flow created conditions that led to higher biological activity. And on these plots, black and gray indicate reference condition and existing condition and reference condition, and annual average values for the exchange flow of phytoplankton biomass or zooplankton biomass. The predictions are almost the same. So the effects of higher temperature are small, and then the elevated biological activity was dominated by higher interannual variability in nutrient loads to the system. And those are our conclusions. Thank you.